Now that we've learned how to put some molecules together, let's learn to take them apart again and put them back together again. And the energy is going along with that. So we're going to talk about bond energies. And again, there are only two types of bonds in this course, ionic and covalent bonds. Let's talk about ionic bond energies. And the name we give to them, the name is crystal lattice energy. And the symbol is delta H sub CLE for crystal lattice energy. And the crystal lattice energy is going to be associated with a very specific reaction. The crystal lattice energy is going to start with, let's say this. Whatever we're doing the crystal lattice energy for is going to be the product. So there's our sodium chloride. And the two reactants are going to be gaseous or gas phase ionic forms of each of the ions here. And so those are going to be sodium plus in the gas phase plus chloride minus in the gas phase. So, and this will be delta H CLE reaction for sodium chloride. And the question might be, what is that energy? But let's see, before we talk about how to get that energy, I will note that this, like ionization energy and writing an electron affinity reaction, and a couple other types of reactions, this is one of the reactions that you're going to have to write for this class. And the clue is whatever its crystal lattice energy is for, that's the product. And then whatever ions you need to make that, those are going to be in the gas phase as your reactants. And our process for this is something like this. So imagine that you're trying to make a solid phase, and your reference state are isolated atoms that are not interacting with anything. Anytime you want to think about something that is isolated by itself, has no attractions to anything else, you need a gas phase atom. And in this case, you need a gas phase ion. And then you put them far apart so they are not interacting. And you imagine a process, and this is an imaginative process. But good news, we have a way for calculating the energy of imaginary processes we can't normally do. Of course, that's called Hess's law. And we're going to use Hess's law later on in this lecture outline. But for now, that's the process. Take gaseous ions that are infinitely far apart and non-interacting, and then allow them to come together. That is our image of the bonding strength for an ionic bond, the bonding energy, and we also call it the crystal lattice energy. Now we can do this for magnesium bromide as well. Remember, take the magnesium bromide. It's in the solid phase, and put ions over here. And for example, so this is going to be magnesium 2 plus in the gas phase. Sorry, I forgot to switch back there. There we go. Magnesium 2 plus 2 bromide minus in the gas phase. And the one other thing is when balancing these, you always have a 1 for the product, because you're always making 1 mole of product. And as we've seen before, the delta H is in terms of, is always per mole, and we want to make sure it's per 1 mole of our products. So this would be a delta H CLE crystal lattice energy reaction for magnesium bromide. And I guess I should put solid there for both of those too. Of course it's solid because it's a crystal, but rather be over expressive than not expressive enough. Before talking more about how we estimate those, let's talk about bond energies for covalent bonds. These are going to be called bond dissociation energies, or delta H BDE for short. And for this, This is a very engineering approach to things. Each type of covalent bond has a typical or average energy for making it or breaking it, called a bond dissociation energy. And the bond dissociation energy is a process by which you take, for example, two chlorine atoms and make, two chlorine atoms that are bonded together. And we could draw the Lewis structure for this now. Cl2 would look like this. And then the bond dissociation energy is going to be the energy for breaking a bond. And we're going to break this bond. And when we break it, we're going to make two chlorine atoms. So each of these gets one of the electrons in the bond. So now we have two chlorine atoms, like so. And whenever you break a bond, the process is endothermic. It always takes energy to break bonds. We saw that when you bring two atoms together, they lower their energy. When you take them apart, you're going to raise their energy. You're going to need energy to do that. And so delta H BDE for a chlorine-chlorine single bond is 243 kilojoules per mole. And we don't have to memorize this number. We are given this number on our conversion and equation sheets. And this is a table on the second page on the back side of all of our familiar equations. It's called average single bond dissociation energy in kilojoules per mole. And hopefully I've got it right here. Chlorine. Oh, this says it's 242. So we're one off. Close enough. Now the same process, and we definitely say it's positive. The same process now for hydrogen will yield delta H bond dissociation energy for a hydrogen-hydrogen single bond is 436 kilojoules per mole. And that I know is correct on that sheet. And then you can start to do single carbon single bonds, and actually delta H BDE for a carbon-carbon single bond should be, 347 kilojoules per mole. And again, all of these processes are for breaking bonds. If we wanted to take two chlorines and make them back into a Cl2, so make the bond, all this does is flip or reverse the reactants and products. And, we can't call it BDE anymore. We just have to call this delta H reaction, since it's the opposite. And it's going to be minus 243 kilojoules per mole because we changed the sign. Now, bond dissociation energies can be used to estimate delta H of reaction. These are estimates because we're using aggregate numbers, and these estimates are best when all the materials are in the gas phase, because gas phase molecules have no other attractions to other molecules, and so we can focus just on bonds being made and broken. And the process goes like this. So when given a reaction and asked to estimate delta H of reaction, step one, you draw Lewis structures for all species. And by species, I just mean reactants and products. And this is a simple example. It goes like this. Here's hydrogen. Here's chlorine. These are Lewis structures. So you must draw all electrons for them. And then here's 2 moles of HCl. Now, for each type of bond, look at your list and do your delta H, B, D, E. And H, as we said, is 436. I'm having a little bit of difference here. Should I just use 242 or 243? I think as my sheet says 242, I'm going to go back and change this to 242. We'll see what influence that has on my other lecture outlines. And then, so I'm going to call this 242, and these are in units of kilojoules per mole. Now I have to look on my list for our first heteronuclear bond. Hetero means different. Bonds, or nuclear means nuclei. So if I look for HCl, I get 431. And now this is a bond that's being made, so it's a negative number. So these are bonds broken, so positive, takes energy, and when you make bonds, those are, so these are going to be bonds made, negative, releases energy. And then all you do, so let's see, I guess that was step 2, do the bond dissociation energies. And then step 3, let's see, add, well, let's say this, multiply by coefficients. And add all numbers. Add all numbers. Which is different than when we did delta H reaction from delta HF values. That was products minus reactants. One way of looking at this, by the way, is that this is reactants minus products, although I find that fairly confusing, but maybe that will be helpful. But you have to keep the two things separate. What I find most helpful is that these are bonds broken, so they're positive. These are bonds made. Then you're going to add up all the numbers. And so what this is going to look like is 436 plus 242 for the reactants. So, and I like to draw a little line here. And let's see, 436 plus 242. I get 678 kilojoules per mole. And that's the energy to break all the bonds of the reactants. And now here we have 2 moles of bonds being made. So this is going to be minus 862 kilojoules per mole. And again, this is energy to make all bonds of products. And now delta H reaction is going to equal 678 plus minus 862. And those are kilojoules per mole, and I will put my units back in a second. It's killing me. I get minus 184 kilojoules per mole as our estimate of delta H reaction for this reaction based only on average bond dissociation energies.